I've been a radio amateur for many years, 40 years, since I was just a little kid. And in the last 6 years, because of an opportunity that arose that I could access a very large dish where I lived in Monterey, once it was made available to me, I said, well, I wonder if we could use that dish for something, satellites, or it's way overkill for satellites, but it's could be used for MoonBounce. So I asked the new private owner of the dish. It used to be a ComSat dish. Everybody remember in the olden days when they had something in Paris or Beijing or whatever, it was live via satellite from Paris. That was a big thing. And it was largely carried by satellites, geosynchronous satellites throughout the world. As technology marched on and economics changed, the means of getting TV coverage now is largely on fiber optics. So the dishes are out there and frequently very underutilized. So like the Jamesburg dish that I found and got to use simply for the asking, there are other dishes out there in a similar way that that can be had maybe just for the asking, or at least used just for the request. And in Mexico, I'm sure there's a number of those kinds of dishes. So some that I have my eyes on are in Tulancingo. Tulancingo is a big Earth station. It was created for the Mexico Olympics, 1968, because the Mexico had to be tied into the world in a broadband way with TV. So that was the target date that they had the Tulancingo Earth Station up and running. So let me tell you a little bit about, some people don't fully understand, or it's not automatic that you understand what MoonBounce is about. MoonBounce is the communication between two people on Earth whenever they can both see the moon at the same time. So you can also talk to yourself if you think about it. It takes about 2.5 seconds from the time you say, "Hola, moon," into the microphone until the time you hear your own voice coming back from the moon, and it sounds the same, "Hola, moon." And it's pretty profound. Even now, I smile whenever I'm at a station and we can do that. And with very large dishes, it enables voice to be done, voice communications. Prior to, or if you don't use large, high-gain dishes, you have to resort to more narrow-band modes that'll function better in noise, like Morse code. But modern kids don't get too excited about Morse code anymore. So we're going with very large dishes, anywhere from 10 to 30 or 40 meters in, 40, that's right, 10 to 40 meters in diameter. And what I'll tell you now, tonight, is a case history of about 4 of those dishes that I've been able to work with for the last 6 years. The first one that I was able to use was at Jamesburg, which is near California, Monterey, California. And we set that dish up for MoonBounce. Took us about, it's all volunteer labor and on weekends, but in a couple of months after we first saw the dish, a team of people from Silicon Valley and myself were able to figure out how to equip the dish for MoonBounce. That means we transmit and receive. The dish itself originally was on C-band, a different frequency than we used. We used 1.296 gigahertz, 1296 we call it. So we fixed the dish up, assessed it, figured out how to drive it, how the original computer that was still working drove the dish. We had to track the moon. We had to know where the moon was and track it from both ends of the line. And then it took us a fair amount of work, but we got it up and running to do MoonBounce. It was quite unusual because it's exceedingly rare for radio aficionados or amateur radio operators to access large dishes. And this was 30 meters. Most home-built radio aficionado MoonBounce stations are something in the order of, if they're dishes, 2 meters, maybe 3. A really ambitious and well-heeled amateur could maybe do a 10-meter dish on rare occasions in their backyard. That's rare. So a 30-meter dish is extremely unusual. It's welcomed throughout the world whenever people hear that it's going to come on the air. So we used Jamesburg, and then a year later, we had an opportunity based on the success at Jamesburg. We used the SRI dish at Stanford. It's owned by Stanford Research International, and it's by the Stanford University in Palo Alto. That's a 46-meter dish. We'll show you some pictures of all these dishes. They're very spectacular and photogenic. So after the Stanford 46-meter dish, we made a request, and it was granted to use Arecibo, the biggest dish on the planet. It's 305 meters in diameter. 305 meters in diameter. So I was really surprised that we were able to use it. So we did sort of well-publicized events because of the specialty and the rarity of the dishes. And we got written up in New York Times magazine. They sent out reporters when we used the Stanford dish. And it creates good publicity. So I thought, after realizing how good publicity and how exciting it was, to bring it out of the Morse code and very, very difficult forms of communication, when you could talk to the moon, it might be interesting to be used in an educational environment to teach space communications. Because if you learn enough to do MoonBounce, you learned a lot of the essentials of orbital mechanics, tracking objects in space. You learn about path loss, how much energy you need and how much gain of your antenna you need to bridge the distance to your target, in our case, the moon. Anybody know, everybody remember, anybody know how far the moon is away from us now, roughly? 250,000 miles, roughly. And I guess that's 400,000 kilometers each way. And it varies. It's not constant. It's always varying from an apogee to a perigee. So let me move down and get to the pictures, which a picture is worth 1,000 words. And actually, I'm in a foreign language to maybe large numbers of you. I hope you can follow what I'm speaking of, and I hope that the translator is doing a good job. They actually are doing an incredible job translating. So I've got my eye on Tulancingo as a potential site to do some MoonBounce. And somebody else took a picture of one of the two 32-meter class dishes at Tulancingo, which you can see in front of you. We need power. We're going to need power soon. Why do we not have power? I had a power cord over here somewhere. Still need power. Just a minute. Houston, we got a problem. Wait a minute. Here's power. Gee. Never mind, Houston. We got it. Okay, so that's one of the two 32-meter class dishes at Tulancingo. Been in communication with Tulancingo a bit, and it turns out the large dishes don't have a high demand to be used anymore. You don't need 32-meter dishes for most of your satellite and telecommunications needs. So they're lying fallow. They're frequently unused, which is a good thing. And there's a ground shot of Tulancingo. It's mostly populated with many smaller dishes to do the same job that the big dishes used years ago. Now, one of the things that we can do with large dishes and high power in amateur circles that's very new, it's only a couple years old, I'll say, is MoonBounce reflect images, JPEG files. You pick a file, any image you got that's JPEG. I got software that'll send it to the moon and come back. Now, it comes back with a patina, I'll call it, some noise that you can see in this picture. And does anybody know this picture? This is Yuri Gagarin. It's a logo that Yuri's Night. You should all look up Yuri's Night on the internet because it's a fun time and parties all over the world on the anniversary of Yuri's first orbital flight. So during Yuri's Night a couple of years ago, I bounced Yuri here in this image and got it back and sent it out to the management of Yuri's Night, and they never knew about it coming. And when I explained to them that we bounced Yuri off the moon and he's back, they went nuts. They said that was cool. That was really cool. So as far as academics or education, there's a lot to be learned from this picture. You see the scan lines. It's a raster scan picture. It takes a minute, a little over a minute actually, to paint one frame. So this is voice bandwidth. This is not terribly high bandwidth like television. It's about 1 minute to complete a picture, kind of like a facsimile machine. And the station that we use to send it is in Dwingelo, Holland. This is a picture of the station that we use. This is an 85-foot dish, which is these classes of dishes. People are beginning to find them and begin to use them for MoonBounce. So it turns out this one was the original dish, the only dish, radio dish in Europe, the year that it was built. I think it was 1956. And it was the first major radio telescope dish built in Europe. And being as old as it was, the ham radio group that converted it to MoonBounce discovered it needed major structural repairs that were very expensive and would have put them out of business, except that the state of the government of Holland decided it was a cultural landmark, and they footed the bill over $1 million to refurbish it. So it's like new now. Just recently got back on the air. Okay. Let's see. I skipped an audio file we got here. Let's play a short YouTube video that shows what it looks like at the station to MoonBounce an image. The image we saw like Yuri just a moment ago. Let me play this and you'll see, looking over the shoulder of the operator, what it looked like. Stand by. You're in the, or if this links up, you'll be inside the, here we go. Public domain software, you can get it right off the net, was discovered to function fine for moon-bounced images. And that's a real-time painting of the picture. What do we got here? Okay. So all you got to do is supply a JPEG file to this software. Just pull it off your disk, have the MoonBounce station, press send, and it'll be MoonBounced. Okay, that's enough of that. Let's go back. One thing I forgot. Oh, did I make a mistake? Sort of. Let's go back a little bit, backtrack a little bit, and I'll play the voice of the William Anders, who's the Apollo 8 astronaut. Does anybody know what William Anders, the Apollo 8 astronaut, is really famous for? Extremely famous for? He snapped the picture called Earthrise. And some people say it's the most famous, possibly the most important picture ever taken. I won't argue with that, but that's an interesting statement. Okay, here's another example of a slow scan TV picture that I sent. This is Rosie Hernandez of Guanajuato. She's very interested in space and was involved in the early ideas and of creating a space agency, what turned out to be AEM. She's a wonderful lady, smart lady, beautiful lady, and we MoonBounced this picture of her. Came out as a MoonBounce picture. It's an interesting picture because you can study the quality of the picture if you like. I like to study the original, though, better. That's Rosie, before the MoonBounce. Beautiful lady. Okay, here we go. Earthrise photo. That's the famous photo from William Anders. And just as an introduction, so this is a case history. I created 3 events that were worldwide over 3 years, and I nicknamed them or called them Echoes of Apollo. The first one was done in honor and anniversary of Neil Armstrong's first landing on the moon. And because it's moon bounces are echoes, we just said echoes off the moon, echoes of Apollo. What you'll hear now is an audio tape taken directly off the moon by a MoonBounce station of William Anders speaking philosophically about space, where we should do, what we should do next in the space program. So you'll hear him directly off the moon. There he is. He was talking to me. I was at the Stanford Dish, and a woman who was a writer for Wired magazine. Probably most of you know Wired. That's Lisa Sonne. So that sounds a little scratchy, but for moon bouncers, that's almost a record-breaking quality and clarity of a human voice off the moon. That was exceptionally good. People were really excited to hear that. Okay, well, let's move along. You get the idea? That was for me, that was a milestone in my technical geek life, being able to pull that off. It took 3 big dishes to do that. William Anders was in a telephone connection with a 10-meter dish in Texas that was communicating with the 41-meter dish in Stanford, where I was at. This recorded message was picked up by a 3rd dish that was on the East Coast. So there's 3 big dishes involved to pick up this audio track. Okay. Okay. And to show you the dishes, to show you what we're talking about, the photogenicness of dishes, I'll go through the dishes that we were working with. This is, whoops, This is the Stanford dish at Stanford. Has anybody ever seen this dish before, or driven by it, or been up in the Silicon Valley? It's a landmark in Silicon Valley. Most people in Silicon Valley know that dish very well. And does anybody know the earliest history of that dish? It was basically funded by U.S. government agencies, three-letter agencies, back in the old days of the Cold War. And it turned out to be a good radar dish to pick up, believe it or not, signals off the moon. The three-letter agencies in the U.S. at the time, after the war, discovered that Russian, they were the bad guys at that time, communications could be heard bounced back off the moon if you had a big dish. And the military applied that discovery to listening to radars, the military radars that protected the Russian border. When they lit them up, and if they were pointed near the moon, we could hear clearly all the characteristics of the Russian radar at that time, which is what we were trying to do with the U-2s and other military airplanes flying around at that time. So this has a really interesting history. It's an incredible place to visit and operate. I was blown away by being able to be in it. The operating room actually literally is in this picture in that shack that's at the base of the moving platform. When we went there and we talked to the director, we were trying to figure out, and this is what everybody in a student environment or research environment will have to do. If you are given permission to use a dish, you'll have to choose the frequency or band that you're going to operate on, and then design or get a suitable feed, the actual feed horn that goes on the dish for any given frequency. That job was made much easier for us because they happened to have one that was used for radio astronomy, which was close enough in frequency and design to use on the 1.2 gigahertz that we were planning to use. So we got this horn, which was right off the shelf in their warehouse. Made some things easier for us. And that's that dish installed on the actual prime focus of the Stanford dish. Gives you some perspective of the size of these things. That's me standing behind it. It's got sort of a universal mount. You can mount lots of different kinds of dishes in the same location. And it's critical that when you mount a dish that the dimensions, that the horn of the dish is at the focus, what they call the focus point of the dish. And you should, if you know what it is, if you know the dish geometry and you know where the focus is, you should match the focus within a centimeter in 50 feet. So if you're off by much more than a centimeter, you begin to lose a lot of the effectiveness of the dish. Okay. And this was our workplace as students or as a research project. It's a challenge to the team that decides to take it on, and the professor, let's say, that tries to take it on. And it's mostly a mechanical challenge. The electronics and the optics are easy to figure out. It's just a question of mechanics and mounting and locating the hardware in the correct locations on the dish. So this inside here is a rack for electronic equipment. You've got two high power capacity, low loss coax going back to the receivers, and a mount for the antenna. We, as a team that had to design the feed, this is the hardware package that we created to mount to the Stanford dish. What you see on the left is the low noise amplifier, extremely sensitive and very low noise amplifier, connected to a series of relays and coax connections that allowed us to create what they call circularly polarized feed. And we won't get into that, we don't have the time, but circular polarization is frequently used in any space communications. So we just built this thing up, tested it, and we have two connections that go to two different locations on the feed horn at the dish. And building that up is is a significant amount of work. If you have all the test equipment, building that up will take you about 3 weeks of volunteer part-time labor. And there's a picture of it, the dish and the horn and the relays all mounted on a bracket at the base. So this is pretty straightforward stuff for any double E. And I could see something like this happening at Tulancingo if we ever got permission to use Tulancingo. Another picture of it mounted and from a different angle. Again, the dish was 46 meters, 150 feet in diameter, one of the largest dishes in North America. This is a little bit far away shot of the feed point. You can see accessing the feed point is always an issue. How do you get up at the feed point? In the case of the Stanford dish, it has a unlatchable bolt that you can electronically unlatch, and then a winch that will lower it to the ground, so you can work on it on the ground. It's very, very safe and very convenient. And that's the dish. Actually, during our MoonBounce weekend, I was taking a walk on the jogging trails. It was above Palo Alto where the dish was. Here's another dish. This is a privately designed and built dish by a private owner in Texas, and it's 10 meters. 10 meters is about as big as they come for homemade, home-located dishes. And 10 meters is a big project. That's a major, major dish. That was the dish. This dish was the one that you heard William Anders' voice from the moon. That dish was pointed at the moon, and we heard it from another dish that was eavesdropping during that conversation. Okay. One of the other major MoonBounce events that we created involved the University of Tasmania. And these could be potential partners to Mexico universities if they wanted to play in the MoonBounce. This is a 26-meter dish dating probably from the Apollo era, and it's run by the local university. And they had some fun working with us on the MoonBounce. So we communicated with them from, actually, the dish that communicated with them on the event was in Holland, that Dwingelo dish. And Holland communicated with these guys, and it was set a world record. The Holland dish that was copied perfectly by these guys at this dish was running 3 milliwatts power. That's less power than a key ring flashlight. And somehow you got that kind of electromagnetic radiation through a dish, two big dishes, to have enough energy at the receiving end after 500,000 miles to receive. It was a digital mode, and it was like texting via the moon. And the text came out even with 3 milliwatts, 3 1,000ths of a watt. Other people do MoonBounce, and historically other people started the whole MoonBounce, and of course it was militarily motivated way back in the 40s and 50s. And one of the leading R&D entities ever, anywhere, is the Naval Research Labs, and this is their headquarters building in Washington, D.C. I didn't know it. We found one of these photos, and I said, wow, look at that dish. What's that used for? And it does turn out it's been used for MoonBounce, for various military experiments. Okay, here's a bit of the geometry that you're up against when you're doing MoonBounce. The moon is a half a degree wide. If you look at the moon, it's a half a degree wide. So if you have a beam and you're creating a beam pattern with a big dish, anything that's broader than a half a beam is totally lost. You'll never get any of that energy back. So whatever you can do to make your dish big enough and your wavelength small enough to create a half a degree beam width is the best match that you can possibly get to your energy to the moon and back. It just turns out 30 meter class dishes at 1.2 gigahertz create a half a degree beam. So we've used Jamesburg and those kinds of dishes, and it's a perfect match. It illuminates just the whole moon surface and nothing more. Even when you illuminate the moon surface and nothing more, the part that gets back to you, that's reflected to you, is a very small region in the dead center of the moon. Think about a basketball from 50 feet away, and you're shooting a cannon with tennis balls at the basketball. Only the tennis balls that hit dead center are going to come back to you. The others are going to carry them off somewhere else. Okay. If anybody knows dBs here, the path loss, which is an essential element of any MoonBounce or any space communication, the path loss in MoonBounce is, you would think it's totally impossible to work with. 273 dBs from the transmitter to the received, back to the received antenna. 273 dB. It sounds impossible to work, but it does. Okay, one of the other stations, actually the first station that started me on MoonBounce was Jamesburg. This is the Jamesburg station, still in Monterey, near Monterey, California, and it's awesome. It's nice to be able to say that you were able to set up and operate a MoonBounce station at this location. And if you want to look at it in detail, there's a good website. It's called jamesburgdish.org. We went there. They had a welcome sign. It was run by AT&T for about 35 years. To show what Jamesburg, what it did in history, it was a crucial link for the Apollo 11 moon landing. One small step for man, that happened. And Jamesburg didn't pick it up directly off the moon. A station in Sydney, Australia did. And the Sydney, Australia station, once it picked it up off the moon, sent it back up to a geosynchronous satellite, Intelsat 3. And that satellite beamed it back down for distribution worldwide to Jamesburg. So once it got into the telecom system at Jamesburg, it was easily distributed worldwide. But if it wasn't for Jamesburg, and if there were no other stations, there might have been other stations available, but Jamesburg was chosen to distribute the Neil Armstrong landing on the moon worldwide. And there's a picture of it from the side. The picture doesn't do it justice. If you go there, it's an experience. It's big beyond belief. That weird-looking metal thing on the back, I thought might have had some sort of an RF function, some radio function. Turns out, no. It's a wind deflector, or wind neutralizer, that lessens the stresses on the dish when it's windy. So we did a lot of inspection and design work before we came up with our own feed. We designed from scratch a feed that was suitable for that dish for MoonBounce. And here you see the outside part of it, of the horn of that dish. And it's literally tin snips and aluminum that we use to create the feed horn for that dish. It probably cost us $200 of materials. The original feed horn, which you'll see in another picture, probably cost $250,000 that was used for the dish, for the original dish use. And there's a picture. That's a picture looking down the throat of the original feed horn. And what we dropped ours, it turned out all the geometry and dimensions were suitable, that we could drop ours right down the throat of that, and it would be correctly located for a MoonBounce feed. Another view. And when we built it, we built several different designs. One of them was totally enclosed and contained behind a piece of plexiglass that kept the weather out of it. And literally it was C-clamps and pieces of aluminum and all that, and it worked. The engineers at AT&T would laugh at that, say that never worked, but it did. And like I said, it cost us probably $400 to build it. And this overall dish, the overall feed, very complex. I was told by people in the telecom industry would be probably $250,000 to build. $250,000. There's a picture. We had a Cassegrain dish. The optics were Cassegrain. And in the process of building a MoonBounce system, you have to look at the optics of whatever dish you're going to adapt. In our case, it was Cassegrain. That demanded a certain design of the feed horn, which we were able to do. Other dishes, like the Stanford dish, was a prime focus dish. So it had its electronics and radio suspended way above the surface of the dish. This has the radio and electronics behind the dish in the middle at the vertex. One of the things when you come upon a new dish that you might want to create into a MoonBounce dish, you have to look at the drive system that the original dish uses. In this case, it was a Vertex RSI, very famous maker of control systems for dishes. And we had to study the manual on that. Basically, we used existing software on laptops that communicated serially to the existing original controller. So we basically said the moon is here. We know where the moon is on a second-by-second basis. And so we just wrote a program that said the moon is here now, go to there. Then wait 30 seconds and say it's now here, go to there. And the original tracking computer handled those commands pretty easily. And so that's how we tracked the moon. So this picture below is just to try to give you an idea of the complexity and precision and scariness, literally, of working around these dishes is. You got a hatch that you can use to crawl through and work up on the top surface of the dish. And when you think about all this structure, all these welds and bolts and all that, there's probably not a single 90-degree angle anywhere. Not a single 90-degree angle anywhere in that whole mesh of support structures. So I cannot fathom how they managed to get this to be accurate, to create a surface that's accurate within about 2 millimeters of the mathematical parabola. 2 millimeters, 2 credit card thicknesses maybe, is how accurate the surface of the dish is. Okay, once we set up the dish and built the feed, we used existing or built equipment, high power RF equipment, and placed it at the focus of the dish and operated literally at the focus. And this is some of the custom-made, homemade gear. This is a transmitter, high power transmitter, which was actually adopted from cell tower equipment. Surplus cell equipment is modifiable to become high power MoonBounce equipment. One of the things that we were able to do was find a surveyor whose specialty job was to measure the residuals, the differences between the perfect dish and the existing dish. And his computer-controlled measurements created this residual images with exaggerated deviations from the dish, mathematical dish surface. And these three represent three different 30 degrees, 45, and 90 degrees elevation. They want to make sure the dish stayed true no matter what angle to the vertical it was pointed. And here's something that gives you a little appreciation for the structure and the precision of the aluminum and steel that keeps that dish correctly shaped. To me, I looked at this closely, and I know why they cost millions and millions and millions of dollars to build. The challenge for any university program, if you're going to take over a dish, is to check out and repair and commission the dish. In this case, Jim, one of our guys, had to repair some of the control cables on the dish. So you see him sort of a nuts and bolts kind of thing where he's doing that. This shows the laptop on a table next to the main controller with a serial cable telling the dish where to go to track the moon. The scale of such dishes mechanically is also pretty awesome to see. This is the ring gear for the azimuth, and the transmission that drives the ring gear is originally, I was told, originally designed for rudder control for big tankers. A big oil tanker, and they turn their rudder. the transmission and the motors go through almost exactly this kind of a transmission. And there's the business end of the motor, about 25 horsepower motors that drive this thing. It's coupled through a chain, so we were able to remove the chain for various testing purposes. Okay, the last big dish that I've operated at was at Arecibo, which is another mind-bending experience. That's the entrance to the Arecibo dish. That's a picture that I took of the Arecibo focus platform from a distance, from roughly the perimeter of the dish. It's really beautiful. If any of you get to vacation or do business at Arecibo in Puerto Rico, get in touch, give me a call, and I might be able to get you an insider's tour, which is mind-blowingly interesting. Scale, see that dome at the bottom? That's called the Gregorian feed. From top to bottom, just of that dome is a 5-story building, just to give you an idea of the size. Here is the director of the observatory and a technical guy and I walking back from the focus platform to the little ham radio shack, which is right where that cursor is, that little blue awning, about 1,500 feet away. And if you go to the focus platform, if you're allowed to, or if you can schedule a visit, it's not for the faint-hearted. It's a lot of catwalks that bounce and move a little bit as you walk on them, and you're 450 feet above the ground there. The frequency we used at Arecibo was 432 megahertz. That's 70 centimeters. Everything in microwaves and antennas proportionally gets smaller or larger depending on the frequency. And I've never seen ever again waveguide, which is how we connected to the Arecibo dish via a piece of coax that comes up from the bottom. This is a coax to waveguide adapter that goes to a piece of waveguide that goes all the way to the dish. It's mind-blowing. This is the actual ham shack that we used, that we created and built for the MoonBounce. A lot of high-level guys, in fact, high-level. See the guy here in the maroon shirt? That's Joe Taylor, probably the world's most famous and best moon bouncer. He's a Nobel Prize scientist. For his real job, he looks at pulsars and got the Nobel Prize for that. So it's fun to see somebody like that in a ham shack playing with MoonBounce. Of course, it's at Arecibo. Look at the red tube upper left in that picture. That's a klystron. That's a radar power tube. Arecibo has the most powerful radar on the planet. 2 million watts output. When they turn the thing on, they have to alert everybody on the whole site and have to inspect to make sure people are not in various hazardous areas because of the radiation when you're talking 2 million watts. So that was kind of mind-blowing. Oh, there it is. There's the 2 million watt final amplifier. The director, at that time, the director of Arecibo, looking on, and a technical assistant. That's, I think, 3-inch fire hose that has cooling water that cools the tube when it's running at 2 million watts. And we had a problem. Houston, we had a problem at the Arecibo, and it looks, I just took pictures of guys' concerned faces when something wasn't working right. There's a story behind that, but we won't get into that now. So there's just more shots of the ham shack and the operators, Joe Taylor, Angel Vasquez on the right, and Jim Breakhall, professor at Penn State on the left. About a month before we were there, before we got there, we were informed there was an a real Houston, we have a problem. A crack happened. There was a loud bang that a lot of people heard on Arecibo and said, "Whoa, what was that?" And it was a structural member that you see in the repair covered in primer paint. So they had a structural failure that really caused them a lot of concern. They didn't know exactly what happened. They traced it down and were able to fix it. Another shot from a distance. It's a beautiful work of art and science. Mike, the director of Arecibo, standing on the very top part of the focus platform. And that's us on the focus platform walking from the perimeter down to the center. And actually there's several pictures here. You can see the stairwell. Proceeding down the stairwell, there's a pivot point. There's a bearing that the whole top focus platform pivots on. Massive. And more shots operating. The shot here is this horn here is the 2 million watt radar. Think 2 million watts would be like 2,000 high power microwave ovens. That's how much energy is coming out of that. And because of all that energy leaving that one single spot, the little bit of losses that are in the horn itself, it's water cooled. You can see the tubing, the water cooling tubing, just to cool the horn down when it's operating. This is a picture of the gondola, the elevator that gets you up to the focus platform from the ground. This is a picture of the focus platform from the ham shack. It's 1,500 feet away in that shot. What do we got? Oh, there we go. Maybe we're close to the end. Let me emphasize that the meeting yesterday, the MoonBounce workshop, to me, I was really happy, thrilled with how well it went and the interest shown by people. And I would like to get some momentum and energy going to create something like a MoonBounce Association of Mexico. Get students and professors and radio aficionados in the area interested enough to do some intensive efforts to put to use some of the dishes around Mexico in a university environment or simply fun radio aficionado environment, but with university backing. We could put Mexico really on the map worldwide if we could get some of the big dishes and the right equipment together to do that. So my objective is to interact with you guys, get in touch, and plan and approach the right people to see if we can get MoonBounce. By the way, MoonBounce costs far less than a single CubeSat shot. For way less money than a single CubeSat, which might last 6 months in the sky, you can build a world-class MoonBounce station that would serve you for 10 years. And it would produce good education and technical feedback on a weekly basis. You could do all kinds of different experiments that you like, anything you want to dream up, and you got the MoonBounce station, and you can use it. So, and the actual capital cost for a MoonBounce station, if you already have the dish somewhere, is probably $15,000 US. Launch fees for a single CubeSat can be $100,000 just for the launch fees. And you might have that CubeSat, might never have it because it might not make it to orbit. If it makes it to orbit, a lot of the design lifetimes are way less than a year. So if you needed to make an economic argument for trying MoonBounce, which is great education in space communications, think about it. It's way more cost effective, in my opinion, and backed by facts, than a CubeSat launch. Keep the CubeSats going too, but a MoonBounce system in the university control would be a great addition to Mexico. Okay, any questions? And in fact, since we're running short of time, we're going to be around here for another couple of days. We'll be at the bar later tonight, probably. Feel free to come and join me and friends, and we'll talk more about MoonBounce. But if there's any on the floor that you'd like to ask, I'm happy to answer questions.